Welcome back to the last unit of the lecture part of COMP335. We'll talk about empirical science and statistics today because this is how you properly evaluate ideas and hypotheses and theories in education. So we'll touch a bit on that. My goals are to give you some vocabulary again, similar to the theory chapter on motivation and learning theories. There are just a few terms that will pop up if you read papers about this that you should, well, at least know where to look it up. And yeah, we'll see how much statistics you've seen before in a second. I think there's some principles that you can say about this qualitatively without getting into much of probability theory that are useful to know. Maybe this will be a repetition for some of you, we'll see. And I'll point out some pitfalls that relates or ties into the pre-session activity. I would say because computer science is not really a natural science like physics, chemistry, biology, we don't have a proper module about empirical science, the scientific method, all these methodological things in our curriculum. It kind of just fell off, I think, or maybe it was never really part of computer science. Also, one reason is that computer science is a weird discipline in that it is half-half. One part is a structural science like mathematics, where you wonder what is possible in principle and how can you make this happen in a theoretical space. And there it's a lot about proving theorems, and everything is on a mathematical model to start with. So you don't need empirical science in that branch too much. And the other part is at the other end of the spectrum, if you want, in engineering, where you're one step behind the natural sciences. You apply certain tools and techniques, and then people teach best practices. I mean, we have software engineering that literally has this in the title, but other subfields are similar. Machine learning is maybe a reason why it might make sense to put a bit more emphasis on empirical research in computer science because it's growing in importance, and that has more similarities to other natural sciences maybe. But yeah, as far as I know, the curricula of computer science courses, they don't really talk much about this. And I do think there's something lost in not covering it. I asked you how much you've seen about this in the past, and I don't know, does the one who said yes want to disclose what module that was? In what context? Yeah.
It wasn't university. I did adult psychology, which had like massive section in school research, which covered all this sort of stuff about hypothesis and this is how they research in the science world.
Yep, that's great. So just for repeating for the recording, you did A-levels in psychology, and that had a more substantial part on research methodology. That's true, especially the softer parts, the humanities or social sciences, they much more rely on this, and also because they often deal with much more expensive things. Generating data is much more expensive in these areas. They have to deal with smaller sample sizes because they can't bring 1,000 people in their lab to test a little hypothesis. And so they have to be even more rigorous on the methodology side, and are hit harder by the replication crisis in a sense. Especially psychology was the field that's always mentioned first in these things. And yeah, I'm not trying to point this out as a field where things are done wrong more often than in other fields. This happened to all fields basically. But it makes sense in psychology to talk explicitly about this. I think it makes sense to talk in computer science about it. If you evaluate algorithm performance, you might as well do this empirically as opposed to just proving big O bounds, which in many cases are not so useful for predicting what's good in practice anyways. But okay, this is more my plea, and it doesn't help to tell you this. Maybe you want to take this forward into school curricula if you ever end up designing curriculum for universities. But let's today just do a quick overview of this space, and I hope it's not too superficial or boring for you given your prior experience. I want to just point out in the beginning, we'll talk about all of these terms on the right in their scientific meaning today a bit. I just want to bring this slide early to say, be careful, all of these terms are used in everyday language, but they mean a different thing. We say theory if it's something that's not really clear, it's just a hypothesis or some suspicion that we might try to show, and it has a much more concrete meaning in science. Same thing for experiment. It could mean anything where you try something is an experiment. That's not true in the scientific sense. Statistics often in day-to-day speaking means you just summarize data in some way. You compute the averages and standard deviations for the marks in your class, and that's the statistics of the class, or the statistics of a population. You compare income or whatever, you know all details from examples of this. In empirical science, statistics really is about the testing part. So you want to make concrete predictions about hypotheses, whether they are supported by the evidence or not. So it has a lot more to do with probability theory, with prior beliefs, with inference. It's in a sense a narrower field that has more algorithmics in it. All these statistical tests are basically telling you what to do to come to a certain conclusion. And everyday language is more a vague collection of things you can compute. And yeah, significant. We say significant if something's big or important in a general sense, but statistically significant has a very specific technical meaning. And especially in popular science reporting, one has to be extra careful to keep those terms separate. So that's also true for your essays. I think your essays can be written in something like day-to-day lingo, as I called it here. But when you talk about experiments or about papers that talk about these empirical scientific methods, make sure you're separating the terms clearly. I think it's often clear from context which one is meant, but if you take a quotation out of the context, then things get a bit hairy. Okay, so let's start from the beginning, in a sense. We'll talk about the scientific method. The scientific method is the philosophy behind science, how we generate knowledge, at least since the Enlightening. And before that, there was often more guesswork, and people felt this is supported by God or whatever. At some point, people started to make this a bit more structured. And the model that we still basically follow is this. You have some observation that you make about the real world, and it gives you food for thought. There's something. I'll have a running example later. But basically, maybe this is an observation you could have made in teaching. If you give students a choice what to do in an assessment, they do better, or they like it better, and then they do better. Maybe this is an observation you've made. Then you can formulate a theory why this is the case. So we talked about motivation theories. Maybe this is something that one can use here. But then you would like to, the theory itself is just in your head, and it's not clear if it's correct or not. So to test the theory, you derive a hypothesis. That's a more concrete prediction. If the theory was true, certain things should follow from it, and these things are measurable, observable. The important tag phrase here is that hypotheses in this sense, they have to be falsifiable. It must be possible to refute them. We'll come back to that in a second. Then we design a scientific experiment, ideally a controlled experiment where you can infer the causation to test that hypothesis. And well, if you're kind of lucky in a sense, or if the experiment has good enough quality in the data, you can support your hypothesis, or you may fail to support it. And then that might lead you to new observations, and so the thing goes round. An important point is that the scientific method itself can never prove that the theory is correct beyond doubt. It can only collect evidence and collect more evidence, and some theories have been standing since decades, despite researchers collecting more evidence, and it's all in support of the theory. That's great, and then we can have confidence in the theory, but you cannot prove it correct. That's just a fundamental limitation in the sense of science in itself. You can refute theories quite convincingly. That's a bit of the asymmetry here, but you cannot prove a theory correct. You can only support it with more evidence. What's the deal with falsifiable hypotheses? I just listed an example that's not falsifiable. If you claim there is an almighty God somewhere, I may try to find evidence for such a God. Maybe I don't find evidence. So I can tell you I never found evidence for your God, so he or she doesn't exist. But you can always say this just has been the will of God, so he or she prefers to be out of sight because he's almighty. He can do it. I can never counter this argument because this almighty is kind of a cheat out of any rational argument. Why I didn't find evidence? You can always take this further, and you replace God with magician, or many other things work. So there's no possible evidence that I could collect that would convince you that your hypothesis is wrong, and that's a problem. And it's not the problem of you, it's the hypothesis itself is just not amenable to the scientific method. Another thing that in practice will plague us usually is that the world is not black and white. Evidence is usually not perfect, and it can usually only give us a certain tendency. Is this more in support of the hypothesis, or more against it? But there will always be a bit of fuzziness involved, or a bit of personal belief. That makes it sometimes hard to make definitive statements, and science is all about being precise and accurate. But then if you want to communicate it, it's nice to have simple statements. So there's a tension here. A way to make this quantitative reasoning rigorous is statistics. It doesn't do away with the belief part, as you'll see later, but at least it gives us a solid foundation for making the quantitative part as reasonable as possible, say. So here's my running example again. I started from the theory here and left out the observation, but I gave that verbally before. So say you believe in the theory that we talked about in the motivation chapter, the expectancy value theory. You assign, you're motivated to do something if you have reason to believe that you succeed and it appears valuable to you to do it. And one aspect of that is if you have choice, if you're in control of the process, whatever you're doing, learning in this case, that improves your self-efficacy, and that improves your expectancy of succeeding. It's a bit of a stretch, but it's often counted as part of this theory. And hopefully, so this is another little stretch, if you like. I'm equating you're more motivated to do it, so you will also be better. That's another claim that one would want to test in an experiment, but let's ignore that for here because outcomes are easier to measure, so it's clearer to talk about this data. And from that we can derive a concrete hypothesis, which is if I give you a choice for your assessment, you'll have better marks. And usually if you state such a claim in a scientific context, you want to be very specific or very careful about the context. Usually the experiment you make will only make a statement for exactly the context in which you tested it. So it might depend on what you're teaching, what field, what type of subject is it. Is it university? Is it school? Is it a compulsory course that everyone has to take? Is it something that students do after school, where it's just those that are interested? All these things will have an influence. So you have to take care to note this. On the slides, I will leave it out. I will just use this hypothesis. And in your head, you will always duly add that it's specific to a certain environment that we're testing. But let's just pretend we leave this out. How can we test this hypothesis? The gold standard for doing this is the controlled experiment. And here again, controlled, it has a specific meaning. It works as follows. You take your subjects, your class of students, say, and you randomly assign them into two groups. And this random assignment is very important for the reason that statistics will pick up later. But in a sense, intuitively, you don't want to end up with all the better students who are more motivated anyways in one group and all the other students in another group. Then you already have a difference between the group. You want the groups to be as equal as possible at the start. And so the best we can do without having perfect knowledge about all your students is to randomly assign them and hope for the best. So we'll have an experimental group, and they do what you think should give them an advantage. And you have the control group. The experimental group, in our case, gets the choice which of two topics, say, they write about, and the other group is randomly assigned some topic. You probably want to control for how often each topic is picked. So maybe you want to give that group the choice first, and then assign the other group the same number of topic A, same number of topic B randomly to people. But the important difference is that the second group, the control group, doesn't have a choice. They just get told what to do, as is maybe still the standard. Then you do with both the same assessment, you mark it in the same way. This is the part where it's important to be meticulous to the methodology. Don't make any difference between the two groups. Ideally anonymize it so that it's blind for you. You don't know which group you're marking at the moment. You will have heard the term double-blind study. That's for medications. If the patient knows they're getting the placebo or they're getting the actual treatment, that influences how they think about it, how they feel, and that, again, could be an influence on the study. So you try to make it double-blind. Neither the patient nor the doctor knows if they're giving the actual new medication or the placebo, just to make sure that these psychological effects are excluded. Obviously, in a case like this, where we assign topics or give students a choice, there's no way we can do this double blind. We can do the marking blind, but that's the best we can do. And then, well, you look at your marks, and if you feel that the marks in one group are better than the marks in the other group, then you have found some interesting difference. Concretely, if our hypothesis was that choice makes the marks better, then if that is indeed the case, we support the hypothesis, otherwise we refute it. The catch here is that better is not so easy. What exactly does that mean? You will get a range of marks from both groups, a list of marks, and you can take the average, or you could take the median, or you take the smallest and largest, or there's not a priori the right or wrong way to do it, but a natural thing is to look at the average. But even then, if you find the averages, these are real numbers. Say you give marks between 0 and 100. If the mark difference, the average mark difference is 1, is that a finding, or does that just mean this is the random variation that you get with a class of people who are not all identical? In a perfect world, you would just take your class, clone it, and have two identical copies for the experimental and the control group. But alas, this is not usually what you can do. So you need statistics for judging if better is better enough or sufficiently better for your hypothesis. So again, same hypothesis as before. Now, one step back, I don't know if you've ever thought about this, I said before, the scientific method can never prove a theory correct. You can only refute hypotheses convincingly. How can we apply this to our hypothesis if all we can do is refute something? Well, the solution is a very nice trick. You apply the whole thing to the negation of what you want to prove. And that's what people call the null hypothesis. So if you want to prove that there is a substantial difference, okay, I'll comment on this in a second. If you want to prove there's a substantial difference between your two groups, the one that got to choose the topic and the one that was assigned the topic, the negation is there's no such difference. And more concretely, we could say the average mark in the two groups is equal. That is the null hypothesis. You kind of don't believe that, right? Otherwise, why would you do this experiment? At least you wouldn't gain much if it was true. But we apply the scientific method to refute that null hypothesis. And if we can successfully refute that, clear evidence that contradicts the null hypothesis means evidence that supports the negation, the alternative hypothesis. And in our case, the alternative hypothesis is, well, the means are not the same. So a slight nitpick. Originally, from our theory of motivation, we would say if there's a difference between the two groups, then the one with the choice should do better. But a priori, it's not clear. Maybe they do worse, right? Who knows? Scientific testing, statistical testing, becomes much easier if your null hypothesis says equal as opposed to lesser equal. That's why I made this change here. So our hypothesis now is there is a difference. If you give people choice, they do differently than if you don't give a choice. And you can then, from the data, often deduce if the difference is positive or negative. Okay, so far so good. Now I've just shifted the problem. How can we refute this null hypothesis? Again, idealistic, if we want to make a statement that's true for arbitrary humans, maybe we should test them all, and then we would know for sure. In a sense, statistics is only necessary because we can't do that. If in some situation you're in the lucky position to be able to test anything and everything that you're making a statement about, I mean by test, include in your experiment, then you don't need any statistics. But yeah, again, alas, it's not what we can do. And we would have to do the experiment twice with roles switched and all that. So to keep things, yeah, a census is a nice example where we do actually have all data about the entire population up to people not responding, etc. But you're obliged to, right? So unless this is an option, you can only take a sample of the population. Maybe in the class, in the example I gave, it's the class of students you already have. And then you never quite know if your sample is large enough or if it's representative. And so we have to deal with the uncertainty that comes from this. And it's also partly baked into the controlled experiment. I said randomly assign the two groups. Well, there's a small chance that you were very, very unlucky with your random assignment, and it did create a very uneven distribution of academic ability in the two groups. But we don't expect this to happen if you have really large groups. It's absurdly unlikely. But how much exactly is absurdly unlikely? And that's why we need statistical tests. All right, so what are statistical tests? Unfortunately, this is where things become complicated because there's many of those tests. But I tried to break it down to a simple abstract formula that's kind of true for all those. And then there's the details, maybe not so important for us because you're not trying to run your experiment next term. You're just trying to understand existing experiments. So that's a bit of an easier task. The two hypotheses and how they are formulated, like in our case, H0 was the means are equal. You could have many, many statements of different types. Maybe you want to test the mean of one is smaller than the mean of the other. Or you can say the null hypothesis is both of these populations have a distribution over the marks, and the distributions are the same, but I don't know what the distribution is. If you're talking about sample means, you can use central limit theorems and assume if the sample's big enough that it's approximately normal distributed. That's what most tests basically rely on. We use not the entire data set in every little bit, but instead we take sample means and how they behave. That's what most statistical tests are about, but there's others. So what are the hypotheses? How do they look like? What forms do they have? And then you get the observations from the two groups. So I call this XC for control and XE for experimental group. And the statistical test computes this ominous p value, which is the likelihood that you see this data if you repeat your experiment many, many times, including the randomness of choosing people and assigning them to groups. If you repeated your experiment many, many times, what's the probability of seeing the data that you got if you assume that the null hypothesis is true? Okay, so you make the assumption, it's kind of a proof by induction, experiment by induction, or, well, reductio ad absurdum for the Latin-speaking people. You try to assume the thing you don't believe is true, and you try to derive a contradiction from that. In our case, contradiction means what we see is very, very unlikely. That's the contradiction. That's the best we can get. It's only in terms of probabilities. And that's what the p-value expresses. I just want to stress again, it's a weird quantity. It's the probability, well, yeah, the proper term in statistics is likelihood because it's not really probability, but it's kind of the same. It's how likely is the data that you've got, assuming something that's probably not true. It's kind of a weird quantity. And that's also why it's hard to interpret. So what people usually do is they just set a cutoff. If the p-value is smaller than a certain magic constant, and that can be 5% in psychology, 1% in some other fields, in elementary physics, statistical physics, it might be much, much smaller because they can produce much more data. But this is something that people have to decide on, and there's no right or wrong. It's just how much evidence do you want to see before you're inclined to believe a hypothesis that this data is supporting. So the p-values are hard to interpret, and so people do something simple, just a cutoff. If it's below, it's statistically significant, and if it's not, it's not. And especially interpreting things that are not significant are tough. I think I'll come back to that as well. Here's a few tests that you might have seen if you've done some statistics before. There's many, many more. And I don't feel this is useful for us because it depends on exactly what you're observing and what you know about the data you get. For example, the difference between the C-test and the T-test is, do you know the true variance in your population? You observe marks, and they will be, if you pick a random person from your class, that is a random mark that you get. What's the distribution of that? It has some mean value, some expected value, and it has a variance. And the difference between those two tests is, do you know the variance for sure, or do you not know the variance? Okay, in our case, we probably don't know it. Yeah, it's the variance of the test statistic. I'm digressing. I didn't want to talk about the tests, so I won't talk about the specific tests much. The basic principle for most tests looks like this, though. We compute some number, and that number is taken, we use our observed data, and we subtract what we would expect if the null hypothesis was true. That's some difference between what we actually have and what we would expect in this universe that we want to refute. And we divide this by the average variation. So intuitively, if you see a very big difference between what you actually got and what you expect if the null hypothesis is true, that makes your test statistic big. And a large test statistic means a small p-value. So this is strong evidence. If the variation, though, is really, really large in your data, then even a big difference might be meaningless because it's just random. If the variation is huge, a huge difference can also just come from random variation. Whereas if the variation is small, it's, again, a bigger test statistic. And the variation includes the sample size. So the more people, the more subjects you have in your study, the lower you can push the variation. Okay. In our concrete example, we probably want to use a t-test, maybe. I more want to focus on saying what the data is in this abstract formulation. The observed data in our case is not simply all the marks of the two groups. It's more specifically the difference between the average marks, because that's the quantity we're interested in. Our hypothesis says the average mark in the two groups is different, and the null hypothesis said no, it's the same. So taking this difference between the averages, that's really giving us the quantity we're looking at. And the expected data in this case, when we assume H0, is just 0 because the difference is not there. Okay? And this is really often the case that this is 0. And well, average variation, if you assume the variance in the two groups is independent, the variance adds up, and then what we need in the formula here is the standard deviation, so it's the square root of that. Well, or you look it up in case you need this. And that gives you the test statistic, which is some number. So that number by itself is really hard to interpret. In this simple example, you can work out the p-value kind of analytically. There's a closed form in a sense. We're computing the p-value from the test statistic. In other cases, you can do this numerically. It's not such a big deal. But there's a mapping between test statistic and p-value that you still have to do. And the test usually tells you how to do this. And that's where the tests differ, and the part that I don't want to talk about. Okay, so that's on one slide how statistical tests work, or significance tests work. And that's what most of the studies use in one variety or another. The devil's in the detail of using the right tests and coming to the right conclusions from it. And that brings me to what can possibly go wrong. Here's an obvious one that you will be familiar with, but I felt I cannot not mention it. If you cannot do controlled experiments, your options are kind of limited. And sometimes controlled experiments are just not an option because it's absurdly unethical. You may have heard of this urban legend, I think, or yeah, it's called the forbidden experiment. The theory is what happens, what's the natural language for children if you don't talk to them? If you raise a child without ever talking to them. You've never heard about this? There's a Wikipedia article about it. Allegedly, this experiment was done 4 times in history, but historians question that it's ever been done. And the results in all the 4 allegedly done experiments was so similar that people are suspicious they might have just copied and claimed it. But the story goes, pick your favorite historical king, takes a few children, puts them in the room, he gives them everything they need physiologically, like food and drink, etc. And there's a midwife, etc. They're taken care of, but no one talks to them. And the story goes, they all die. Now, we don't know if this is really true, but it will definitely damage the children, and no one wants to repeat the forbidden experiment, so maybe we'll never know for sure. This is a tough one to approach in any other way because, well, we don't have much evidence of people rising without any outer influence of language. And sometimes it's just absurdly expensive and we still don't want to do it. I mean, there's many examples of things we would like to know, but a controlled experiment is just out of the question. You can still do something. You can do an observational study. That's what's done a lot just because it's cheap. The data is there anyways. I don't know, what's a nice example? Okay, I listed our widening participation data set. You can look at postcodes. There's data that shows you how many people go to uni. There's data how many people from the postcode have certain income. And then you can try to connect these two. Is there a correlation between income of the postcode area and, well, the number of people going to uni? I wouldn't be surprised if there was a correlation. Now, what can you do with this? And that's the problem with these observational studies. You only ever get correlations. So one variable and the other have a relationship. If you increase one, the other also goes up. But this is not a causation. It's just the pattern in the data. Whereas causation is if you change one thing, the other will follow. That's a subtle difference, but yeah, I mean, you've probably seen this before. So we can probably expect a correlation between income and higher education participation just for many reasons, unfortunate as it is. But we cannot infer from this data anything that, you know, having more money brings people into university physically as a direct consequence, or that university degrees generate higher income. Both is not unplausible, but we cannot conclude this from this data. And maybe you've seen this website. I don't have this as a link here. Well, it doesn't matter. We're running a bit out of time. So it's a website that just goes through publicly available data sets and finds highly significant correlations between two things that most likely are just random. For example, the number of people who drown is highly significantly correlated to the number of movies with, I think, Nicolas Cage in that year. So you look at the two curves and they nicely follow each other over many years. Okay, it's probably just random luck. The thing is, if you take enough pairs of things, you will find some significant correlations. That's almost guaranteed. But that doesn't mean much. Another thing that could go wrong, there's lots of issues with how studies are done and how empirical science is done. I wouldn't be as cynical as this headline of the video suggests. I think it's not quite as hopeless, but definitely one has to be careful, and there are some incentives that are seriously misaligned. Judging the worth of scientists by how many papers they put out or how much waves and fuss the papers they put out create gives them an incentive to only publish these kinds of results, and that bias alone is harmful enough. A big discussion has been, as a result from this, whether one would want to ditch entirely this notion of statistical significance. Especially if you pick a threshold like 0.05, you accept that with 5% your result is a false positive. The null hypothesis could not actually be refuted. Well, the null hypothesis is actually true, but your data refutes it because you were lucky enough to get one of the 5% outliers. 5% is 1 in 20, is not so great. Maybe this is not so useful. And yeah, this binary classification of significant, not significant, or insignificant, significant is maybe not as useful. And yeah, you can do all your statistics proper. If your study is flawed in the setup, that won't help. And yeah, the video had a nice example. This chocolate makes you lose weight, where they just designed the study so that it leads to this outcome. I think you've seen it all. Maybe the point where we want to show this. Okay, that was the explanation of the p-value, and that's the one I wanted. Okay, have people check each other. Yeah, the bias, that's absolutely, that's partly done, making sure people register studies so that even if they fail, they get reported. Larger samples increases the cost, so yeah, I'm up for it. Yeah, peer review in principle should work. There's a lot of flawed incentives there as well. It's a thankless task that is not paid for and usually not recognized much. Yep. Yeah. Okay, yeah, seems people are interested in this. It's definitely an important thing to fix. Yeah, I think this is a big point as well. One has to live with the fact that not every study is new and exciting, and we should reward this, even if it's just for making scientific knowledge more rigorous. All right, the last thing I wanted to list again is misunderstanding what p-values give you, because still, even if you say we don't really want statistical significance as a binary concept, the p-values are useful, but they're easy to misinterpret. And so they're still the best thing, the best tool we may have, maybe together with Bayesian inference, but they need to be interpreted carefully. So just rephrasing, same thing as before, the p-value is this weird thing. It's how likely is it to see the data if you assume the hypothesis that you want to refute is really true. So if that p-value is large, what that means is basically you haven't learned anything. It doesn't mean that the null hypothesis is true. In particular, the p-value is not the likelihood that the null hypothesis is true. It's just it's not. It's something different. It's the likelihood of your data given the null hypothesis. But there you already assume the null hypothesis is true. So you can never get a statement from there saying something about how likely it is that this is true if you already assume it. Nevertheless, you see this kind of as an implicit reasoning many times. Just don't do it. The other thing is, yeah, be careful about what is exactly the null hypothesis and what does refuting it imply. In our case, it said the mean is equal, so refuting it means it's not equal, and you might have statistically significant evidence for that. So your data is very strongly supporting that the means are different, but it doesn't tell you how much different. It doesn't even tell you the direction of the difference. So whether it's significant in the everyday language meaning is not clear and needs to be analyzed separately. Okay, I think that was a lot of material, even though not much mathematical detail. Do you have any questions about this for now?